Welcome to Special Relativity Lesson 1. Aristotle mistakenly taught larger and heavier objects fell faster than lighter and smaller objects. This was a popular point of view for well over 2,000 years. Galileo came along in the 1600s and proved that all objects in fact fall with the same acceleration. Therefore, the longer an object moves with constant acceleration, the faster the final velocity. In a pure vacuum, Galileo also stated that two objects of different masses will hit the ground at precisely the same time at the same velocity when dropped from a rested position, or velocity equals zero. Combine this with Newton's law of motion, which he developed using calculus, and this gave birth to modern science. Let's focus on a rule that Galileo came up with, Galileo's principle of relativity. Now don't confuse this with Einstein's relativity. Though closely related, it's not the same. Galileo stated that it's impossible by mechanical means to say that we are moving or staying at rest. Two trains are headed down a track at the same rate. A person in train A looks over and sees a person in train B. The person in train B is looking back at the person in train A. Both of them are accelerating at a constant acceleration. Because of this, they cannot tell without outside influence such as vibrations that they're either moving or at rest. The only way to tell whether they're actually accelerating or staying at rest is by being a guy on a platform staring at the trains. If he noticed that they're moving away from his fixed point of view, then they're definitely accelerating away from him. That's the only indication that they would actually be accelerating. Have you ever flown in a plane? Well, if you have, and you've actually got up out of your seat while you were in a plane, you would notice that when the airplane is at a constant acceleration, that you can actually safely get up and walk around inside of the plane without much effect. Let's talk about inertial systems. Newton defined the law of motion. A body continues in a straight line unless acted upon by an external force. Inertia is simply the resistance to an object from anything outside of it acting upon it, including a change of direction. An object will stay or keep moving in a straight line unless it is acted upon by an external unbalanced force. Say you roll a cue ball down the table. It would continue in a straight line. That is, until you jab it with a cue, which would push it off course. The cue is the external unbalanced force acting upon the inertial system of the cue ball. Now, named after Galileo, there is an actual coordinate system that can be used to measure these laws in motion within it. This is called the Galilean coordinate system. We will actually talk a little bit more about this at a later time. Laws of Galileo and Newton are valid in a Galilean coordinate system. Earth, the Milky Way, Andromeda galaxy, the universe, all of these have Galilean coordinate systems. If we label the Galilean coordinate system with the letter K, then every other system similar to K is a Galilean system, and thus follows the Galilean and Newtonian law. If we want to observe an effect in a moving system at a constant acceleration, we can apply Newton's laws directly. If the moving system speeds up, or we speed up relative to it, for example, us observing stars from Earth, then we will have to introduce an imaginary force to compensate for this effect. It's almost like looking out a telescope and constantly having to make subtle adjustments to keep an eye on that star system. This fictitious force is called centrifugal force, or also known as the Coriolis force. Newton's law of motion are mechanically accurate for speeds that are slow compared to that of the velocity of the speed of light. For speeds that approach the speed of light, we actually have to introduce Einstein's special theory of relativity. In Newtonian and Galilean physics, the quantities used to measure moving objects are the same throughout the universe. That is, unless they're approaching the speed of light. In those cases, we must introduce Einstein's special theory of relativity. Now we've set the stage to introduce special relativity. In our next video, we'll be discussing the four-dimensional space that we have all come to know as space-time. We'll also discuss the universality of the speed of light. Thank you for taking time out of your day to watch this video. If you liked, please give a thumbs up to the video. If you want to see more, subscribe to my channel. I'll be introducing them about once a week. Until then, this is RJ signing off from the New World Classroom.